Okay, so let us start. So till now we completed, like we got to know that how to find like what is capacitance, where it is utilized, and what is the capacitance of a spherical conductor. Then we got to know what is the dimension formula. Then energy is stored in the capacitor. Till here we did, isn't it? Okay, so after completing till over here, 1 minute. Uh, just 1 minute. Yeah. I want to define some of the terms which are very important in capacitors. Okay. And then we will move ahead. Right or not? So any kind of doubt till now? Any kind of doubt from electrostats or something? Are you solving it, Sivama? Completing everything? Yeah. So now you can handle that in a perfect way. Okay. And if you require a tough notes, if you still require something as a tough notes, then you ask me. Is that clear? Means tough, a little bit conceptual notes. Okay. Like if you want another kind of notes, I'll provide you. Got it? Okay. Okay. So before going to talk about too much about capacitors and all, the point is I want to talk now about a specific term which is widely used in physics, and I told you I'll describe in capacitor in a good way. And that term is called as dielectrics. Right or not? May 7th, isn't it? So we are going to talk about a particular term which we call it as dielectrics. Are you able to get me or not? Can you hear me now? Hello. Actually, it's happening due to the network fluctuation. A lot of network fluctuation is there today. Now, can you hear me? Yeah. So look over here. So now let us understand that what is first of all called as dielectrics. Are you able to get me or not? So the first point is a dielectric is also called as an basically it is an insulator kind of object. So we will write that it is an insulator. Okay. And there are no free charges on it. Yeah, no free charges, not free electrons. Electrons are always there. So I am not supporting that it is a kind of a charged object. Got it or not? It's a neutral object with zero free charge and it is an insulator. Are you able to get me or not? So that means that if it is an insulator, then what will happen? It will not be able to conduct electricity, isn't it? So a dielectric is that kind of material which has which is an insulator and there is no free charges on it. That means we can't conduct electricity out of it. Are you able to get me on that? But then the question arises, you might see in various topics we utilize this concept of dielectrics, that let us put the dielectrics between the capacitors and all these kind of things are there in NCERT, isn't it? So the point is that they are actually if we look into the dielectrics, they are divided into two main categories. Are you able to get me or not? Okay. And based upon that property, we utilize the dielectric. So first one is called as non-polar dielectrics. Is that clear? First one is called as which dielectrics? non-polar dielectrics. The meaning of this is that what are non-polar dielectrics? Basically, we call it as, so the the particular dielectrics which have which does not have their does not have their own dipole moment, but under the influence of electric field, but under the influence of external electric field, take they get polarized, they get polarized and show some dipole moment. So look over here. Basically, the point is, you know that what is the work of electric field? It dissociates, it makes the charge here and there or not. You can imagine, let's suppose if I take an atom, okay. So inside the nucleus of atom there is positive charges or not. But outside it, in a normal way, we have the electron cloud, isn't it? Now in this particular object only, if I switch on an electric field, what I do? I just brought a external electric field. Then what will happen with the atom? You know, you know that the positive charges will start orienting towards the electric field or not. So positive nucleus will go along the direction of electric field, but what will happen with the electron cloud? It will go opposite of the electric field, isn't it? So this kind of this kind of some diagram will be like too much electron clouds along the opposite side, while some positive charges towards the right hand side I will get along the direction of electric field. So this means that what has happened actually, some kind of a dipole has appeared or not. One having plus charge, another having minus charge. Are you able to get me? So see, when there was no electric field, there was no dipole, isn't it? But when there is an electric field, there is a presence of a dipole or not. And this kind of objects which shows such kind of property, we call these as non-polar dielectrics. क्या बोलते हैं इसे अपन? Non-polar dielectrics material. Are you able to get me or not? Is that clear? Second kind of dielectrics are, yeah. The second one is called as polar dielectric. Is that clear? The second one is called as what? Polar dielectric. What actually happens that they have their, yes, yes, they have their own, yeah, they have their own dipole moment, but does not conduct electricity. Although they have their dipole moment, means they have the presence of a positive charge and a negative charge, but still they will not conduct the electricity. Example is Na with Cl. Look over there. Na is a positive charge or not? Cl is a negative charge. So this is an example of a dipole or not. But does they conduct electricity when they are in normal form? The answer is no. They do not conduct electricity. Are you able to get me or not? Yes. So they do not conduct the, yes. So they do not conduct the electricity when, yes, yes. So that's why we call these kind of bodies as polar dielectrics. क्या बोलेंगे इनको अपन? Polar dielectrics. Now look over here. When we have non-polar dielectrics, there are some polarization. And if you look over here, there is negative charge and the positive charge. So some kind of another electric field is generated from positive to negative or not. So to talk about that in a much more greater sense, I'm bringing one big important topic, which we call it as polarization of okay dielectric slab and bound charge. Now look over here. Let us imagine something. Let's suppose I have a dielectric slab. Sorry, got it. So what I did, I just took one slab, a dielectric slab, a non-polar dielectric slab, and then means I just put it this in some kind of a external electric field E. Is that clear? So what will happen? This non-polar dielectric slab will get polarized or not? Yeah. Basically, it will feel polarized. And if it is going to feel polarized, you can observe that here my positive charges are there, and towards this side, negative charges are appearing or not? Isn't it? Are you able to get me? Is that perfectly clear? Now, question arises that there were no such external charges earlier, but right now I have some charges or not? So the amount of this presence of this polar dipole moment, which like there should be some quantity which should differentiate between the metals now or dielectrics also, that yes, this body is a bigger dielectric, this body is a smaller dielectric. So the condition is that magnitude of dielectric is measured in the terms of magnitude of dipole moment. Are you able to get me or not? I will once again say the magnitude of dielectric, the amount of the means the more is the dielectric medium, the more is my dipole moment inside that material. Is that clear or not? And that is why we say that the dielectric to talk about that which metal is a bigger dielectric material. So we measure the dielectric property by a dielectric constant. So the dielectric constant of a dielectric material is denoted by K. Is denoted by K, which is also called as kappa in physics. Are you able to get me or not? Yeah. Kappa named kappa. Is that clear? Yeah. So look over here. What you observed over here, that when I have plus and minus charge, another internal electric field is getting generated or not? Yes. We call this as, so there is an external electric field and then there is, yeah, so we call this electric field as induced electric field, EIM. क्या बोलते हैं इसे अपन? Yes. So look over here. Basically, when I have any kind of dielectric in particular external electric field, then that dielectric has two electric fields at the same time. First one is E, and then there is E induced. Is that clear or not? Are you able to get me? No, they can. They will be different if they are in same in magnitude. What will happen? Hmm. Okay. So listen. The question is, see what I am. How does this happen? There is a big understanding of this. So look over here. Let's suppose. Okay, should I go in depth? Okay. Let's suppose if I take any kind of a conductor. Okay. You know that for any kind of a conductor, where my charges are there at the surface. Do you know why? at the surface, isn't it? Do you know why? Why the charges are not inside the conductor? See, if there is a conductor, then it means that the charges will flow in a particular direction or not. So when I have a conductor, what happens? We consider that the charges are at surface. There is a reason for that. That that when you say that if there is any charge inside the surface of conductor, what will happen is that means that there is some electric field inside the conductor, isn't it? If I just include some kind of charges inside the conductor, what will happen? These charges will start moving in a particular direction and they will start generating the particular electric field, isn't it? Yes. So the point is that inside, the point is simple that inside of a conductor, the net electric field is always equal to how much? Zero, isn't it? So it is not possible that if I will put a charge inside the conductor because that conductor will start generating an electric field and start moving in that, isn't it? Are you able to get me or not? So this is the biggest reason that this is why even we consider that for a conductor the electric field is perpendicular to the conductor because there is a reason for that. If we consider parallel one, then this plus charges will start moving inside the conductor or not. And they will move, they will start moving till that time, till their electric field balances with the external electric field, isn't it? So this is why electric field is perpendicular to the conductor. It's not present along the tangential component or along the surface of the conductor. Are you able to get me? Is that clear? Similar is my property of a dielectric slab. That when you put it in a external electric field, it has an equal number of positive and equal number of negative charges because there is no free charges, isn't it? So the positive charges starts to orient in the direction of electric field. The negative charges starts to orient in the opposite direction of electric field, generating an induced electric field inside the material. Yes. So look over here. Then the equation says that whatever is my external electric field minus this induced electric field must be equal to some kind of external another electric field or not or resultant electric field. That resultant electric field is nothing but external electric field by kappa means yeah it is 1 by k times the external electric field basically. Is that clear? External is E, yeah. So we got our relation basically that E induced is equal to E minus E by K, or I can take E common 1 minus 1 by K. Are you able to get me or not? Isn't it? Now look over here, whatever is this E induced electric field that must be equal to sigma by epsilon naught or not? Because it's a non-conducting sheet, isn't it? So it must be sigma by epsilon naught, which is E 1 minus 1 by K. Are you able to get me or not? So from this you can get your sigma or not. So look over here. We can say that we also know that how much is my induced charge over here. So sigma induced is nothing but external electric field into epsilon naught 1 minus 1 by kappa. This is my amount of induced charge. Are you able to get me or not? Is that clear? Or this is, look over there, since these charges are not moving anywhere, we call this as bound charge. So induced charge का नाम क्या है दूसरा? Bound charge. Are you able to get me or not? Yes. Is this clear? Are you able to get me? So I should write induced charges are only called as which kind of charges? Bound charges. So that means that remember that in if the external electric field is E and the dielectric constant is K, then the net electric field felt by this Dielectric is always E by how much? K. Are you able to get me or not? And then we can write the equation E minus E index is equal to E by K. Are you able to get me? Is that clear? Okay. So now look over here. We are going to utilize this in our concept of capacitors a lot, which will help us to understand how the capacitors are formed and how these are going to be considered as. Is that clear? So look over here. Let us start with. Okay. So first thing, we know that. So till where we have done? Yeah, yeah, yeah. So look over here. Let us suppose. Let's start with the most important thing, which is capacitance of parallel plate capacitors, isn't it? So look over here. That day we discussed, we got to know that how energy is stored. Energy is only stored when you bring two conductors, isn't it? If you don't bring any two conductors, your energy will never ever be stored. Are you able to get me or not? That was our concept or not? So look over here. So the first kind of arrangement we are doing is of parallel plate capacitors. Are you able to get me or not? So let's suppose there are two parallel plates. Okay. Okay. And I just connected them with some kind of a potential. Got it? So when I connect them, they will get some charge or not. Yes, we know that if this is going to get plus Q, this will get minus. Are you able to get me or not? So look over here. Due to this, let's suppose if the distance between the plates is given as D, let's suppose the distance between the plates is how much? D. And surface area of the plates is how much? A. Then there will be some electric field which will be generated from this positive plate to negative plate. And that electric field, you know that electric field is how much? Sigma by how much? Sigma by sigma by epsilon naught, because it is a conducting plate, isn't it? Look over there. We have the condition now that if it is look over there for conducting plate, what is the relation? For conducting sheet, it is always sigma by epsilon, isn't it? Are you able to get me? So look over here. Using this property only, we are going to understand that how to write the equation of particular parallel plate capacitors and all these kind of properties. Is that clear? Now look over here. Let me just see whether they are considering non-conducting or conducting. Okay, let it be anything. So look over here. Let us see. So if it is a conducting parallel plate, then the net electric field is sigma by epsilon naught. Now question arises that how you are getting some. So see, for plus Q, the electric field is in which direction? This direction. For minus Q, the electric field is in which direction? This direction. For plus Q in this region, the electric field is along this direction, while the minus Q, the electric field is along this direction or not. Similarly, for here, for plus Q, it will be away. For minus Q, it is towards the plate. So let us suppose if I mark the region 1, region 2, and region 3. And we know that for one side the electric field is how much? Let us write it in a perfect. Let us prove this statement. For one side of conductor, the electric field is given as how much? Sigma by 2 epsilon. अरे कुछ तो बोलो हाँ ना, यही होता है ना. तो ध्यान से देखो in reason 1, since we know that for parallel plate, for any kind of a plate, the electric field is not dependent on distance. So here, what I will get? Basically, the electric fields are in opposite direction or not. So they will become how much? Zero in the reason one. So I'll write in the reason one and reason two. Sorry, reason one and reason three. The innate value is how much? Zero, because they are in equal and opposite directions. Are you able to get me or not? Are you able to get me? So now look over here. So therefore, the point is I'll find the net electric field. The electric field, therefore the electric field in reason 2 is how much? Simple. How much will be that? E net will be equal to, there are two electric fields. So E sigma by 2 epsilon naught plus sigma by 2 epsilon naught. And that's why we get sigma by epsilon naught. Are you able to get me? Are you able to get me? Right. Ah. Okay. So now you see that when I am considering this distance d, then due to this electric field, what will happen? Since there is an electric field and it is perpendicular to the plates, there is some potential difference which will develop over here. Yes. So look over here. I can write the change in potential difference. You know that since this whole plate is it is a conducting plate, so it will be a equipotential surface, and this is also a equipotential surface. So we know that for any kind of equipotential surface, change in potential is always equal to minus of E dot dr, isn't it? So now, if I'm approaching negative potential, okay, so I'll consider since this is minus, so I can write now. Final is negative. So instead of considering negative, I'll consider positive to omit this minus sign. So V plus minus of V minus must be equal to how much? E into distance d, because integral dr is distance d. Are you able to get me? Yeah. So it will become what? Sigma by epsilon naught into distance d. Are you able to get me or not? Now, what is sigma? Sigma is nothing but charge by surface area or not. If the surface area of plates are given A, where A is what? Surface area of plates. So now look over here. I can write it as QD by A epsilon naught, isn't it? But this is potential. So potential, change in potential divided by charge. Can I write it as D by A epsilon naught? But what is C? C is equal to Q by V or not? So therefore, we get the formula of capacitance between two parallel plates as A epsilon naught by D. Are you able to get me? So this is the formula for capacitance when we have which kind of plates? Parallel plates basically. Is that clear? Yeah, write it, write it. Yes, so basically, see, delta V, the real formula will be V minus or V plus. Hold on. But since it is negative over here, so just I have interchanged. Yes, so that's why I have interchanged. Okay, got it? Now look over here. So we got to know that what is the formula of capacitance of parallel plate. So this is how much? Epsilon naught A by how much? D, isn't it? And next thing is, We know that if it is a parallel plate and if I charge through potential V, it will store some energy or not, and that is equal to half CV square. So look over here, after putting half CV square, so if I write energy stored in parallel plate, it is half C V square, isn't it? So I can put this epsilon naught value over here or not? What I will get? Half A epsilon naught by D, isn't it? But what is V? What is V? V is equal to change in potential is QD by A epsilon naught or not? So you can multiply QD by epsilon. 1 minute. अच्छा इसका स्क्वायर होगा ना, स्क्वायर हो जाएगा तो ध्यान से देखो तो क्या है रिलेशन अपने पास, दैट u of parallel plate is given by formula, this and this will cancel and this d and d will cancel, हाँ q square d by a epsilon naught or not. Can I just write this as half q square a epsilon naught by d? Are you able to get me? Then we got two important things, two formulas of parallel plate. That C of parallel plate with air in between it is given as A epsilon naught by D. Without even finding the potential and charge, we can find the capacitance of the body, and then the potential is stored, means energy is stored between the parallel plate is given as half Q square by C. Are you able to get me or not? So this is the concept of parallel plate capacitors, which has capacitance how much? C, and the distance between them as D. Write it fast. Okay. Now try to see that. Oh, sorry. What can happen? Let's suppose I took two parallel plates capacitor. But what has happened actually that they are not present perfectly parallel with each other. Okay, they are not present perfectly parallelly. Means this plate, okay, this plate is can be seen that actually look over here. This level of the plate is what? This, isn't it? That's my level of plate. Are you able to get me? So instead of this level, let's suppose the plate is present at, let me just mark it like this way. The plate is present little bit down. It's not present over there. It's present over here. Are you able to get me? Okay. So it's not present perfectly up. It's present where little bit down. Are you able to get me or not? So then the question arises that how you are going to find the capacitance then, isn't it? See, if I know the total, see, if you look over here in the previous case, they were perfectly parallel. Distance was the total surface area, whatever this was covering, this was also covering the same, isn't it? But here, what has happened? Here, they are not perfectly matching, isn't it? Look over there. What you can see that some part of the region is present only, isn't it? Like this much region of this is occupied by this much region of this parallel plate capacitor. और कुछ तो बोलो है ना? यही है ना बस. So then the concept is for these kind of parallel plates which are not perfectly coinciding, You are only going to consider the capacitance between that region which is overlapping. Are you able to get me? Other part you are going to neglect always. Yes. Yes. So look over here, let me write. If the plates are not exactly in front of each other, if the plates are not exactly in front of each other, then if I use C is equal to A epsilon naught by D, then A is that area which is overlapped. Area is overlapped area is considered. A is the overlapping A. Are you able to get me? Is this perfectly clear? Okay. Got it. So look over here, we got to know the capacitance of two kinds of capacitors. One is a spherical capacitor, which was given as formula 4 pi epsilon naught R, and another one is parallel plate capacitor, which is given by formula epsilon naught A by D. So till now we have two kinds of capacitors, isn't it? Capacitance of parallel plate without dielectrics I'm considering A epsilon naught by D, and capacitance of spherical plate, which is equal to how much is that? 4 pi epsilon naught into R. This is all this always these all are always getting done because of only one formula which says that Q is equal to CV. Are you able to get me or not? Yes. So look over here. Let us imagine one another case. What if instead of, let's take one question. Instead of a single spherical plate, I have a coaxial spherical plate. Got it? Outside it is vacant, inside it is vacant. Is that clear? And this has, let's suppose if this has some radius r. So let me draw. Inside radius is r1, outside radius is r2. Got it? And this one has plus q charge and this one has minus q charge. This is sphere A, this is sphere B. The question is find the capacitance. Find the capacitance between AB. Do it fast. Should I help? Should I help or can you do? A is, yeah, A is empty. There is no such thing is inside it. Okay, look over here. Basically, how to find the capacitance? Uh-huh. I have to find the capacitance between AB. So first I should find the net potential difference between AB or not. So V of AB is what? V of A minus V. What is potential of A? It will be due to minus Q also, Q also. So potential due to Q is how much? KQ by R1. Then due to minus Q, for see this is an external charge or not, and this is an interior region, so it will be minus KQ by R2. And I told you that day potential is a scalar quantity, so I need to consider the polar plus and minus of the charges. Are you able to get me? So this is V of A minus V of B. So due to minus Q, minus KQ by R2, and sorry, due to plus Q, it is an exterior point. So Q will come at center, so plus KQ by R2, isn't it? So V of AB is how much then? This and this will get cancelled, isn't it? So what I will be left? KQ by R1 minus KQ by R2, which is equal to KQ common 1 by R1 minus 1 by R2, which is equal to KQ R2 minus R1 divided by R1 R. Are you able to get me or not? So then Q is equal to how much? CV, isn't it? So C is equal to how much? Q by V. So Q, I'll put K, Q by V is how much? 4 pi epsilon naught Q R2 minus R1 divided by R1 R2, isn't it? Are you able to get me? I have written perfectly now. Oh, shit. I have written 4 pi epsilon naught wrong. 1 by 4 pi epsilon naught now. Yeah. No, I have to write it 4 pi epsilon naught once. So this Q and this Q will get cancelled. And this implies C is equal to how much? Numerator it will go 4 pi epsilon naught R1 R2 divided by R2 minus R. That is the formula of capacitance for which kind of a capacitor? Coaxial spherical capacitance. Are you able to get me or not? Write it fast. R2, R2 minus R. Is that clear? And you can see that the electric field will also exist. Electric field will exist from which to which charge? From inner sphere towards the, isn't it? Now, so I'll ask one exceptional question of this. Actually, it was asked to me in an interview. I remember that question till now. Okay, they asked me that, sir, okay, these all things are here given. You can easily find the capacitance. We calculated three kinds of capacitance till now: sphere and parallel plate, and then coaxial sphere, isn't it? The third one was which they asked me, which was very unorthodox, and it is kind of different kind of a question. Bola, कि let's suppose there are two isolated spherical conductors. Are you able to get me or not? Okay, each one having some radius. As you can see, they will have. Let's suppose this has some radius r and this has some radius I'll call it. Let's suppose this has radius A and this has radius how much? B. Right or not? And this has plus q of charge and this is minus q charge. So I have this as two isolated spheres, two isolated spherical conductors kept at large distance. Then they asked me that find the capacitance. Find the capacitance. This was their question. Find the capacitance. Yes, find the capacitance. What is the what is it is they are placed at large distance. That's what they are saying. They are saying nothing about another thing. Yes. Do you think what will happen if we consider the large distance? Is it really means does the large distance concept is really going to affect us or it's just for uh, they have just utilized for namesake? Think 1 minute. Try to think. You think whether it is for namesake or whether it is really affecting anything. चलो अब देखो बनाते हैं समझते हैं थोड़ा what it is asking. Two isolated spherical conductors are kept at large distance and then we are required to find the capacitance, isn't it? So let us see what is the meaning of this. ठीक है. What is the basic meaning of this? What is the meaning that if I say two isolated capacitors at large distance, that means this gap between them is of no use. This distance between them is of no use because yes, that this large distance has not any kind of a meaning because we do not know that particular distance. Are you able to get me or not? And another meaning of this is that the potential of this sphere is not affecting the potential of another sphere. Are you able to get me or not? Interacting. They are not interacting. So we will not consider the interacting potential. So look over here, write this term that I am taking class. Bye bye guys. Okay. So look over here. So point is bye 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 bye. So these are my friends who are calling me right now. So I have to remind them I'm taking class. So look over here. If I have isolated any kind of a body at large distance, that means they are not interacting. First meaning is that they are not interacting. So there the potential. This means that the potential of one sphere will not affect the another sphere. Affect the other sphere. Just like in previous case, we used to find potential of A was what? It is due to plus Q and minus Q both. So this time it will not be like that. So potential of, let's suppose this is a sphere A, this is a sphere B. So potential of A will be what? Simple KQ by A, and potential of B will be minus KQ by B on the surface. So if I take VA minus VB to find capacitance, it will be simple KQ by A minus of minus KQ by B. So this is KQ common means Q by 4 pi epsilon naught, and it will be AB or R1 R2. In numerator it will be A plus B or R1 plus R2. Are you able to get me or not? So instead of negative, so we know that Q is equal to what? CV. Yes. So let us put over here C into B, which is Q by 4 pi epsilon naught A plus B by AB. Is that clear? So this Q got cancelled, and this time the capacitance is given by formula 4 pi epsilon naught A into B divided by A plus B. In terms of R1 R2, 4 pi epsilon naught R1 R2 divided by R1 plus R2. That's your capacitance. So this is the meaning of things which are kept at large distance. Is that clear or not? Must concept है ना? These are not available in any of the books. If you search it in a random way, you have to think, you have to imagine why sir gave us this question, that what is the meaning of large distance, isn't it? So you always have to think over there. Is that clear? Yes. So we did a sphere, we did large distance also, we did the parallel plate. The last kind of capacitors which we have usually, we call it as cylindrical capacitor. So give the heading capacitance of cylindrical capacitors. So let's suppose I have a cylinder, like you know that I'll have to consider one field, one non-field, not field, isn't it? Are you able to get me or not? Okay. Or should I draw linear? Let me draw the linear one. Middle it. Simple 2D one. So I have, let's suppose, okay. So is this clear? So I have one plane, then with that inside it, so it's not fully filled, okay? It's only little bit filled. So, Wow, I'm good at drawing the diagrams. Control C. So look over here. Can you see this cylinder? Okay. So inner radius is given to us. Let us bring the axis. So this is the axis of the cylinder. Okay. Okay. From the axis of cylinder, let's suppose the inner radius is how much? R1, and outer radius is also given R2. So inner radius is R1, outer radius is how much? R2, and the length of the cylinder is also given, which is L. Okay. The question is, if this is plus charged and this is minus Q, then find the capacitance of the cylinder. Think and do it. Do it fast. Uh-huh. Inner cylinder is hollow, outer cylinder means there is, see, basically, if I am defining, I'm not putting anything. Here also, this reason which I have taken as a filled reason, I'm considering that this is a kind of a air reason. Okay. So we are considering till now all the that kind of systems which are vacant, hollow kind of systems. Are you able to get me or not? Second, inner one is also hollow, outer one is also hollow. It's like cylindrical cells. Okay. Then find the capacitance. Do it. Think. Imagine. It's easy peasy and cheesy. Acha, you tell me. Cylinder. What is the electric field due to the cylinder? I told you, no, it's similar to the rod, isn't it? Lambda by that's your electric field. See, the point was I told you that day that okay, first thing we are considering these cylinders as, let's take one assumption we are taking, that these cylinders are infinite. Yes. So first consideration is these cylinders are infinite, isn't it? So we know that potential at infinity will not be this time equal to 0. So that means I will have a change in potential from R1 to R2 or not. And for infinite cylinder, the cylinder behaves like a straight rod, which is E is equal to 2k lambda by R, isn't it? Are you able to get me? Now, here, if it is plus Q on each length, so lambda will be equal to what? Q by L? Yes. For finite case, not for infinite. Are you able to get me? So, the point is very, very simple, that we are using the assumption of infinite cylinder to solve the finite cylinder. Are you able to get me or not? The assumption of infinite to solve the finite, such that we are considering that we can take these very, very small parts, and for every reason the electric field, there are many electric fields which are generated. Are you able to get me or not? Because then we can only say that the potential will vary from R1 to R2. Otherwise, I'll have to take the potential of reference point to be 0. To be 0. Is that clear? So look over here. Then I can use directly my formula. See, since R is changing, the electric field is also changing or not. So let's suppose if I define the electric field for a some intermediate point, then electric field will be given as what? 2k lambda by a small r, which is 2 lambda by 4 pi epsilon naught r, isn't it? Then change in potential is given as what? Minus of integral E dot dr. Hi, getting. So what I will do? I'll put it, since this change in potential should be positive in nature, so modulus integral minus of r1 to r2 E dot dr. This one I will apply so as to find my net change in potential. Are you able to get me? So look over here, if you put E dot dr, since I am considering it to be positive, so I'll take 2k lambda as outside and integral r1 to r2 1 by r dr or not. But this is negative will become positive now because we have taken modulus already. Okay. So it will become what? ln r, isn't it? So delta V will be what? Simple 2k lambda ln R2 minus ln R1. Are you able to get me? But this is written as what? Log A minus log B is nothing but log A by B. Log R2 by R1, which we have derived earlier, isn't it? So look over here, if I put the V in terms of Q and all, or let us just write in terms of CV. So Q is equal to what? C into V. So C into 2 lambda. Lambda is what? Q by L. और कुछ तो बोलो हाँ है ना? For finite case. And into 4 pi epsilon naught ln R2 by R. Is that clear or not? So this Q and Q got cancelled. And this 2 and 2 will make it 2. So look over here, you got your formula for C. C can be written as what? 2 pi epsilon naught. And if this is 1 by ln R2 by R1, in numerator I can write it as what? Ln. So I'll just write in terms of this only. So 2 pi epsilon naught divided by this will come in denominator ln R2 by R1. This is my capacitance of the coaxial hollow cylinders. Are you able to get me? Is this clear? मजा आया फिलहाल? ठीक है. Now look over here. So this is what happens when we have when we connect two kinds of cylindrical capacitors. Then we will have always this answer in terms of log. So we studied four different kinds, mainly parallel plate, then normal spherical, then coaxial spherical, then isolated, and then cylindrical, isn't it? Now look over here. The question arises to give the heading sharing of charges sharing of charges between two conductors. Huh? मान लो that I just take two random capacitors. Okay, means they are of arbitrary shape. Do not think that they are like of a spherical in nature. Just consider they are arbitrary shape. Good. Yes. So look over here. If this is my first capacitor, which is Q1, having some capacitance C1. So initially this was charged. This was what? Charged with capacitance C1 and charge Q. Second one was having charge Q2 and capacitance how much? C2. Is that clear? Got it. Now what I did, I just connected them with a wire. Now look over here. Then something will happen or not? You know that when we connect anything with the wire, the charge gets redistributed or not? Yes. So question is, find the final charges on both of them after disconnecting them after some time. Find the new charges after disconnecting them. Think, I do not know. You have to do. I have made you understand in electrostat so many things. So you have to reply me what is actually happening. Think and tell me. Achha, look over here. Whatever happens when you connect them with the wire, so what will happen? After connecting, you know that when we connect anything with the wire, then their net potential finally. So V final of 1 will be exactly equal to V final of 2 or not. Isn't it? So V final 1 will be what? Q 1 final, isn't it? By capacitance तो नहीं change होगा ना C1. Then V final 2 is what? Q2 final divided by capacitance how much? C2. Yes, isn't it? The look over it means that finally, let's suppose this one is getting Q1 final. Okay, and this one is getting Q2 final. Are you able to get me? So now look over here, whatever happens, then Q1 final plus Q2 final is always going to be equal to Q1 plus Q2 or not? Yes, they are always going to be this term, isn't it? Because total charge will never change and that will be redistributed, isn't it? So what is the relation of Q1 final? So this implies Q1 final is equal to C1 by C2. Q2 final, अगर कुछ तो बोलो हाँ है ना, इसमें रिप्लेस कर सकते हैं क्या? If I use this first equation, if I replace if I replace it, what I will get? C1 by C2, Q2 final, Q2 final, Q1 plus Q2. So this gives us the first equation that what will be Q2 final? It will be exactly equal to C2 divided by C1 plus C2, isn't it? If I take common, I can write like this way or not? And then multiply it with Q1 plus Q2. Are you able to get me or not? I can take C2 as LCM, so C1 plus C2, Q2 final common, and then C2 will be multiplied over here and I'll get this answer, isn't it? And following this only, we can also write that Q2 final is equal to C2 by C1, Q1 final or not. Replace that, what you will get the equation. So this is first equation. Second equation will be uh, Q1 final plus C2 by C1 Q2 final, sorry, Q1 final is equal to capital Q1 plus capital Q2. So this gives us another redistributed charge. Q1 final is equal to C1 by C1 plus C2 Q1 plus Q2. So this is your charges after redistribution on two different conductors having two different capacities. Are you able to get me? Is this clear? Totally? Yeah. ठीक है समझ में आया है ना ठीक है आगे बढ़े now look over here. So the point is that, like, okay, I'm putting some charge, I'm putting some capacitance, I'm doing everything. Then this capacitors, whichever you are, whatever you are charging or something like that. So when we charge the capacitor, look over here. Let's suppose if I connect this capacitor with some kind of a potential, go ahead on. So give the heading first. See, if I am putting some charge, then I need to charge the capacitor or not. So look over here. See, till now we discussed all the cases when the charge was present and the capacitance was present, isn't it? अरे कुछ तो बोलो हाँ. But the reality is, I need to charge to bring the sorry, I need to charge the capacitor to bring the charges on it or not. So look over here. Let us try to charge the capacitor. So write the heading: charging of sorry, charging of parallel plate capacitor. Now let's suppose I want to charge the parallel plate capacitor. Okay. So I took the capacitor, okay, which had some distance d, and I connected them with some kind of a battery. Okay, nice, isn't it? And this capacitor had some distance d between them. Are you able to get me? समझ में आ रही concept? Now look over here. When I connect with, if this is potential V, this is plus and this is minus or not. So this will start. Look over here. This will start. This will make the capacitor to have positive, and this will make the capacitor to have negative, isn't it? So try to understand that if I am trying to charge it, then plus should come on this plate and negative should come on this plate. Means electrons are moving from this side to this side, isn't it? Are you able to get me? So look over here. When I am charging the capacitor, ultimately I'll draw the electron direction. The electron move from this side towards this side. Okay, like this way. Okay, and due to this, the charging happens. Now, ultimately, you only think if initially there was zero potential, so final potential of the of capacitor will be how much? It will be exactly equal to the battery potential. Ultimately, after sucking all the electrons, it will have final potential to be equal to how much? V only. Battery, isn't it? Are you able to get me? Now, due to this potential, you know that the electric field will be generated between the plates. Electric field will be given by the plates as what? V by distance D. Are you able to get me or not? Now that electric field, you know that the amount of electric field, since it is generating some plus charge Q and minus Q over here, so this electric field will be what? Q by A epsilon naught, which is equal to V by D. Are you able to get me? So charge which is going to get developed due to this will be also equal to how much? The maximum means whenever you charge a capacitor, the maximum capacitance, the maximum charge that can develop is equal to capacitance of the capacitor into the potential of the battery. Are you able to get me or not? So Q is equal to CV was my original relation, isn't it? And it used to say that if I have charge Q, then I will generate some potential. Vice versa is also there. That if potential is V, the charge will be generated maximum and that will be equal to CV. Are you able to get me? Are you able to get me? Now look over here. When I am charging the capacitor, ध्यान से देखो. So I am inserting some electrons or not? So if I am inserting some electrons, it will increase the electrostatic pressure, isn't it? So if electrostatic pressure is getting increased, that means what? The heat will be generated during the charging, isn't it? So look over here, give the heat. Heat dissipated during charging of capacitor. Heat dissipated during charging of capacitors. Are you able to get me? So look over here. Basically, heat is generated by what? Heat will be generated by this, like see, who is doing the work? My battery is doing some work on the capacitor, parallel plate capacitors or not? Yes. So if my battery is doing the work, then it will only generate the heat, isn't it? So look over here. So point is, work done by battery to charge the work done by battery to charge the capacitor will be how much? Q into the maximum charge that will be generated into the potential of the battery, isn't it? Potential which will be developed. So what is Q max? It is equal to exact CV, isn't it? So it will be how much? CV square and kuch to bolo hai na, isn't it? So this is my work done by the, this is my energy supplied by the battery. You can also say that this is the energy supplied by the energy supplied by the battery. But if you see the energy stored by the capacitor, it is equal to half CV square or not?